all for coming. It's a great pleasure and an honor for me to introduce today's ECS Department Colloquium speaker, Dr. Darío Gil. Dr. Gil is IBM's Senior Vice President and Director of IBM Research, which is a major institution of technology research with over 3,000 researchers. Dr. Gil is nowadays working in leading a national effort in quantum computing, but he has a history of many contributions in many areas of technology. I remember him as an expert in integrated circuit lithography, for example. He chairs or co-chairs the MIT IBM Watson AI Research Lab. He's a member of the NSF National Science Board and many other boards like the Semiconductor Industry Association Board and many other positions of influence in the technology community. It's a great pleasure to have him here to tell us about the really spectacular effort that is ongoing at IBM in quantum computing, and he's going to tell us about what's next. So, Darío, thank you.
Well, thank you so much, Jeff, for the kind introduction. And it's been such a joy to be able to spend the whole day meeting with different faculty and see how much energy there is here on campus on so many areas that are of great interest to me personally in the world of computing. So I'll start by, as a means of introduction, to tell you where I work. This is the research headquarters of IBM. It's about 45 minutes north of New York City in Westchester County. This is the T.J. Watson Research Laboratory. And it's a beautiful building. It was designed, we were just chatting about Bell Labs. It was designed by Eero Saarinen, the great Finnish-American architect that designed also the St. Louis Arc. And if you remember like pieces of modernist architecture like the TWA building in JFK and Bell Labs, of course, around that. So in the building we have about 1,400 scientists and engineers who work there. And it's part of, IBM Research overall is a distributed network of laboratories. I showed you Yorktown. This is a laboratory at MIT focused on AI. In California, we have a laboratory in Almaden, a little bit south of San Jose. That is also well known for physical sciences. This is our Albany facility in New York, which is a leading 300 millimeter semiconductor research facility in the United States, where we've done like really beautiful work on 2 nanometer technology and beyond. Our Zurich lab in Rushlikon, also a very well-known place for the invention of the scanning microscope and many other advances in nanotechnology, and that's our Haifa lab in Israel, to give you a flavor. So as Jeff mentioned, slightly over 3,000 scientists, many disciplines. We've always had a whole variety and eclectic community of engineers from every discipline and physicists and mathematicians and chemists and so on. But what brings us together, it's always been a passion for trying to create and imagine new ways to process information, new ways to drive computation forward. Is kind of like the core identity of it, and and I think a wonderful blend from sort of basic scientific advancements, and but also a passion for applying those advances to create technology that makes a difference to the industry. So our purpose really is to invent and to create what's next in computing, and today I'm going to talk about quantum computing. But let me just say that I think this is the most exciting time in computing in probably 60 years. And just the combination of course, exploiting all the power that we have seen from digital technologies and advanced semiconductors, but what's happening with AI, which I'm not going to talk about today, but as everybody knows, is just simply amazing. And then what's happening in quantum, and the convergence of all of these technologies is going to be something quite remarkable. So I like to say that what's next in computing is bits plus neurons plus qubits, right? As a means to remind the power of high precision computation, the power of neural network architectures and reimagining the kinds of systems that we can build with it, and the power of quantum. But the point of making the bits plus neurons plus qubits point is that I don't think we've done anything yet about the possibilities for convergence. and what is it going to mean when we combine all of these technologies for a whole variety of problems. Now, in the context of speaking about the current state and what's coming next in the world of quantum, it's very useful to just briefly go back to the nature of information and the beautiful theory that Claude Shannon and others allowed us to create the modern information technology and computing edifice that we all benefit from. Shannon famously said that information is the resolution of uncertainty. And he was able to codify and introduce to the world the idea, the mathematical representation of the binary digit, the world of zeros and ones. But what was really, really powerful too is it allowed all of us to appreciate that even though you can have physical systems that are as vastly different as a punch card or DNA, that we could actually understand them as carriers and processors of information. In fact, he actually drove a strict separation, right, between the mathematical abstraction of zeros and ones, the binary digit, and its physical manifestation. And that proved that it gave us a lot of dividends because we had the core theoretical underpinning that we could implement independent of whether we had vacuum tubes or transistors or wireless versus wire communication, etc. But that strict separation between physics and information is actually an assumption that gets revisited at its core in the idea of quantum information. So if mathematics and information gave us the world of bits, I think it was an important question to ask by a number of physicists and others that were curious about the idea of, was Claude Shannon right in separating so profoundly physics and information? And it turns out that that is an assumption that was worth revisiting. And the blend of physics and information to start asking fundamental questions about what is the nature of information is what gave us the world of qubits that we're going to be exploring today and the possibilities of quantum computing. So in fact, in that characteristic, I think one important point to make is that it is the first time in the history of computing with a capital C that the field itself is branching. And that moving forward, we will have classical computers, of course, and then we're going to have quantum computers that have to work in concert with classical systems. So as such, it's not right to think about quantum computers as just like another step on Moore's law, right? As just another step on that exponential curve that I've been driving, but as rather something quite profoundly different around that. And I'm going to show you today lots of examples about what the machines look like of the types that we build in IBM and the possibilities. So this is a peek of an assistant that I'm going to show you at the end of the talk called IBM Quantum System 2. But let's begin by laying out some fundamentals of what's behind and what we actually care about building these kinds of machines. And the reason we care is because as powerful as classical machines are, and they're very capable, from a complexity theory perspective, they can only solve easy problems in quotes. Meaning, for problems in which the number of variables grows exponentially, and there are many examples of that in modeling the physical world, as an example, chemistry and physics calculations, but also in mathematical problems that we care about, there are many classes of problems that the number of variables that we have to compute over to get to an answer is an exponential. So, examples of them, there's complexity classes, there's NP-hard problems that have that characteristic, but there's also problems, with a different complexity class beyond NP, like, for example, simulating quantum mechanics itself, that is not only hard to compute, but it's also hard to verify that you have the right answer. What is interesting about quantum computing is that it's, an example of a class of technology that alters the equation of what's possible versus impossible to solve in some of these classes of problems. Notice I'm not claiming that quantum computers can solve all NP-hard problems or hard problems, but rather there's a subset of problems that are of great interest to us that today we can build classical machines that approximate the answers to them, sometimes with enough accuracy to meet the need, but sometimes with not enough accuracy to meet the need, and that is the space in which this technology will be able to make a difference. But In fact, for example, one very famous example of that is the problem of factoring, which is the basis of modern-day asymmetric encryption that we use for all sorts of security purposes. And here illustrates one of the points that sometimes is misunderstood about quantum computers, that quantum computers are not really just faster computers. The question is, it depends for what kind of problem they might be faster. So for example, if you look at the problem of the forward multiplication of p times q and give me the product, quantum computers are going to be much, much, much slower than classical machines. But of course, the interesting aspect of it is that if you ask the reverse problem, if I give you the product made out of two large multiplications of two large prime numbers, now the reverse problem turns out to be exponentially difficult for a classical computer, and much, much faster for a future quantum systems. So the question is, are quantum computers faster? The answer is, it depends. It depends on what problems and how well you map it to. But there are classes of problems in which this is really, really important. So let's build it step by step about what is a unit of representation of information, and what is the nature of an algorithm, and then how do we actually realize this on practical quantum systems. So I'm going to use a very simple representation to give all of you a bit of an intuition for the nature of an algorithm. And we'll start with just imagining that we're going to have a sphere, and that when I put a little moon on the North Pole, I'm going to call it a 0. When I put one in the South Pole, it is going to be a 1. And one characteristic of the qubit, the first principle we'll use, is that we're going to be able to have superpositions of 0 and 1 states. But one characteristic in this representation, these diagrams that I'm going to be showing you, is that one thing I get to do is I get to have a phase present in my little moons around it. So notice here that I've introduced a little rotation on the South Pole moon in here, which is depicted by some blue and red. In this case, it's a full 180-degree rotation. So that we're going to, borrow and take three, areas and principles from physics that we're going to incorporate in how we represent information and how we process information. And they're going to be the principles of superposition, interference, and entanglement. So the principle of superposition is straightforward. We experience in lots of classical systems. So in this case, if I have a 0 state and a 1 state, I can create a superposition of those two states. But remember that one of the tricks that we have up our sleeves is that these superposition states actually have control over the phase of these states. So in this case, I've introduced a Z rotation. So when I have my 0 and 1 state, I ended up with that 0 plus 1 state, but with a phase rotation in the 1. And you'll see why we're going to exploit that phase rotation in a second for a trick. Now, one interesting thing in the world of quantum superpositions is that the state that I create inside these quantum systems is in a very definite state that I have very good control over its evolution. But when you perform measurements, you get random results, right? So you can have random results, and yet, even though the state is indefinite characteristics, and again, we're going to put all of these principles together. Interference is something that we're all very familiar, like waves in the ocean, where you can have peaks and crests, and the cancellation depending on the amplitude of the phase of the waves interfering with one another. So one very different way to process information compared to classical machines where I have transistors and on and off gates is that in this case, if I have a 0 and 1 state in this sphere, and I add it to another qubit that in this case has a phase rotation, I get to cancel things out, and I end up with a 0 state. So this principle of interfering information is an interesting characteristic that we're going to exploit in the algorithms that we can create. Which brings us to the third element that we're going to bring to the table, which is the principle of entanglement. That simply states also that in this case, entangled qubits have the characteristic that we cannot describe them independently of one another. In classical machines, if I know the individual states of all of my transistors, I can make certain representations and claims about the overall state of my machine. In quantum world, like, just knowing the individual states of my qubits will not tell me, right, what the overall state of my entangled qubit machine would be like. And this is rooted, this principle of uncertainty, from Heisenberg uncertainty principle that, is well known by all, of the inability to know with arbitrary precision the position or speed of a particle. So in this case, what we're going to exploit is this characteristic that if I have entangled states or entangled particles, and and I even separate them over arbitrary long distances, if we look at one particle alone, as I mentioned before, even though you're in a well-defined state, the measurement of that particle would look individually random. But if I have entangled particles that have this special property that we've come to appreciate thanks to quantum mechanics, if I actually now perform a measurement in one of the particles, let's say, to measure the position or the speed of one of them, I would instantly know the position or the speed of the other particle, even if they were very, very far apart. So what this tells us is that, a quantum mechanical description of the world is much more complex than everyday experience tells us. And in fact, this property, this characteristic that we get to realize in the quantum machines that I'm going to show you, have an exponential classical cost if I were to represent those states that are available to me in the quantum machine in creating this superposition and entanglements using bits. Meaning, if I had a perfectly entangled 100-qubit machine, the number of states available to me is 2 to the n, where n is the number of qubits. So, if I have 2 to the 100, that's more than there are atoms on planet Earth. Meaning, if I devoted every atom on planet Earth to store zeros and ones, that's how big my machine would be to be able to represent the full state of that entangled machine. So the two fundamental quantum physics principles underpinning quantum computing is this idea that a physical system can be in a definite state yet behave randomly, and that systems that are too far apart to influence each other can behave in ways that, though individually random, are strongly correlated. So, now, the ability to mimic this behavior, as I was alluding to in the classical world, would require exponential resources. And quantum computation, we can look at it as a technology that allows us to access this unique resource that is underpinned by these theoretical ideas. Now, the input to a quantum computer is always classical information. It's just a string of zeros and ones. The output of a quantum computer is also another string of zeros and ones. What is special is what happens in that intermediate representation inside the quantum processor itself, where I get to map that input of a string of zeros and ones to 2 to the n states and perform quantum information computations in a very controlled environment. And in the end, I perform a measurement and I extract information out of the system. So let's put it all together, right, to give you an intuition for how an algorithm works, right, at a high level. So the first thing I'm going to do in a quantum computer is put the machine in a superposition of all its available states. So let's say I have a 2-qubit quantum system. So I get to have 4 states, a 0, 0, 0, 1, 1, 0, 1, 1 state. And that's step 1, right? So however many qubits I have, first step, put in a superposition of all the available states. The next thing is we have to send data into the computer, right? So in this case, in this diagrammatic representation, recall that I have, my different states that I get to put anywhere in the sphere. And, one way to think about how data comes in is to induce a rotation in the states that are present. So I'm going to encode the outside information that I want to compute over by inducing rotations in the states that are present in there. Okay, so now I have my machine in this superposition of states with data incorporated in these phase rotations. And the art of writing an algorithm is to take those states, those amplitude and phases, and be able to evolve in a very controlled fashion the system such that I interfere those states in such a way that the right answer is maximized and the answers I don't care about get canceled out, right? This is this aspect of evolution through interference. So at a high level, that's kind of like the sequence, and I'll just highlight it like just how different it is, right, from the way classical information gets processed. So now you may ask, it's like, okay, so is it possible to build things that like do all the things that we just talked about? And the answer is like, yes, you can. And in fact, one interesting thing about the wide availability of demonstrating these capabilities began also in May 2016 when we created the IBM Quantum Experience that put a small system that had at the time just 5 qubits. And we made it universally available through the cloud, right? So at that point, anybody could sit in front of a classical computer. And what you're seeing here is like an interface where each line that you see here represents each one of the qubits. So that has 5 qubits, and there was a sequence of gates, the sequence of operations that allowed you to create this superposition and entanglement and interference and measurements around that. And then what would happen is you would just press click, go, and we would take the zeros and ones coming out of your classical computer, and we had a machine that we had built in Yorktown. We converted those zeros and ones to microwave pulses operating about 5 gigahertz. They would travel down a cryostat. And through those wires, we would have at the very bottom of the cryostat our 5-qubit processor. And we would perform all those operations that I told you about. We would amplify the signal around it and then return the answer back to the user with zeros and ones. So associated with that, just about a year later, we built an open source environment called Qiskit, Quantum Information Science Toolkit, that allowed this community to start experimenting, right, with both the access to the hardware and a way to develop the code to be able to execute this. And what was interesting around it, we didn't know how many people would be interested in this, right, because it didn't do something that you couldn't do with a classical computer, but it was accessing a unique new resource. And what you're seeing here is the community that has been created since those systems, and we've built over 50 quantum computers since then. And you're seeing here that over 2 trillion quantum circuits now have been run using our network of IBM quantum computers, and close to 500,000 users from around the world. And in fact, it has become an element that is present now in the educational curriculum, right, on quantum information science. I was talking to some faculty here today around discussing how this is also part of the experiences that happen here also at Berkeley. So it's been one of the great exciting things have been a community that emerges and collaborates along the field. So it was part of like a philosophy that we had that this is going to be a journey. Obviously, quantum information theory has been around since the 1970s, and the experimental effort has also taken many decades, and they're going to be many years ahead of continuing to develop this technology. So the community aspect building of it and participating and bringing new fields into this industry is an extremely important element of it on bringing people along and benefiting from the talent and the contributions of many areas. And in fact, you see this from a scientific output perspective. Over 2,000 research papers have been generated now using this new scientific instrument. And you see here sort of like the curve on how that is growing on a whole variety of areas of science and engineering. So you're also starting to see that industrial companies are beginning to explore and form small teams to explore algorithms and applications on 3 broad categories is how I would describe how I would map the areas of interest that you see the most from industry. One is the original sets of ideas that were expressed and articulated by Richard Feynman and others quite a few decades ago, which is, look, if you want to simulate nature, build a machine that works like nature, right? Build a machine that works and operates according to quantum mechanics. So for the industrial sector, for companies that rely on developing novel chemistry, novel materials, novel alloys, and physics developments, you see a whole group of participation, like companies like Boeing or Daimler or Bosch or many others, who are interested on developing use cases and applications that use these machines to develop future products in that space. Then there's a second category that is embodied by financial industry and others that are interested on data that has some complex structure that we want to be able to extract that information. Of course, data with complex structure, I give you an example of it, of like the factoring algorithm. You know, I give you a large numbers, there's a structure in there which is made out of 2 prime numbers, but revealing that has exponential cost with classical methods. But there are other examples of a new field of like quantum machine learning and other areas where that is of great interest as well. And then there's a third category that, you know, does not offer exponential advantages, but, you know, rather more modest advantages that maybe in the future with large enough systems could be exploited, which is problems related to search and optimization, as an example. But, you know, they don't have the category of exponential advantage compared to classical machines. So you see here a whole variety of use cases that you're seeing now this industry and that these sets of companies also exploring. So let's look at, you know, a little bit in the vowels of what is inside these systems and where do we need to go next. And it really has allowed us to rethink quite profoundly the nature of what a computer is and what it could be. The first, you know, observation, you know, even casually, is that they look very different than classical machines. The different ways to build quantum computers. Today I'm only going to talk about you know, superconducting technology, because it's a technology that we use at IBM. And, but there's different ways you can build it with ions, you know, and there's many different techniques, and there's a lot of creativity in the field overall of exploring different, you know, qubit modalities and how they're creating. But today I'll talk to you about superconducting technology based on a device called the transmon qubit. So first is this, you know, these golden chandeliers that look very different. This is the, you know, we're going to go inside them. This is what a Finnish quantum computer that we put around the world. We have systems installed, I mean, not only in New York, we have over 20 of them that we manage through the IBM cloud, but we put a system also in the Cleveland Clinic that is going to go up and running in a few weeks in Germany, in Japan, in South Korea, in Canada, in many places. So this is what you know, a fully integrated system. And inside, they look like this. You see, well, this is, you know, a model of what the inside of one of the previous generation looks like. So you see these coaxial cables. That's where the microwave pulses travel down to. At the very bottom, that's the quantum processor itself. It operates at 15 millikelvin temperature. And, you know, at the very bottom, and you see sort of associating all the amplifiers required with the signal. So we're going to go into the different dimensions of how the technology scales and what are the limitations. And I'll just like to point out how much progress has been made in a decade, right? A decade is a long time in the world of technology. This is what a superconducting qubit looked like in 2010 in Yorktown. And the right-hand side is a 433 qubit processor that has been fully packaged, and we're going to get a chance to look inside around that. So 3 dimensions to put our attention on you know, what progress looks like and where we need to go. And the 3 dimensions that I'll propose for you to consider is scale, quality, and speed. Scale is an obvious one. It's like, well, how big a system can you build? How many qubits can you create? Quality is a measure of, like, you know, how well do they obey quantum mechanics, those qubits that you have built, right? What is the intrinsic error rate? You know, what is the fidelity of those devices? And, you know, there's a metric that have been developed at IBM called quantum volume that incorporates those elements. And then the speed. How quickly can you execute these circuits, right? Because that's very important to be able to run an application. And there's a metric called CLOPS, circuit layer operations per second. So we're going to go and look into these elements around, so you see what is the rate of progress and then what is required on each of those dimensions. In fact, to be able to facilitate and to guide how we were going to develop the technology, we put out a roadmap in 2019 where we basically said, this is kind of our commitment. This is what we're going to shoot for at IBM Quantum. And the way you look at this is that there's a system-level roadmap, and we're going to look at that. That went from, remember, the 5-qubit system in 2016. We said we were going to go to 27, 65. This is year by year, right? You see on the top, 127, 433. This year, we're going to build and break the 1,000-qubit barrier in our processor. And then I'm going to tell you about modularity, how we're going to build systems with many tens of thousands of qubits and what is the underlying technology. And above it is an entire software stack and system stack that goes everything from kernel developers to algorithm developers to model developers. Basically, think about this layer as like assembly language, right? All the way down to engineering pulses, controlling the qubits at the most fundamental level. You definitely have to know quantum physics, and software to operate at that level. So there is a runtime environment. Think about it in like if you're, using and doing a lot of AI at the level of like, what happens with accelerators with CUDA and things like that on NVIDIA, sort of, at that runtime level. There's an algorithm layer above this, and this is, again, you have to live at the intersection of exploiting quantum physics as well as mathematics to develop things like quantum machine learning as an example. And then above it, for the model developers, that's where we've elevated the abstraction and the representation of that information at the level of libraries. No quantum physics required. You just have to know that there is like a library that calls upon these systems. And our ultimate vision of this is that I think it's like something like 25 million people that earn a living writing code around the world. 99.99% of them, we better develop systems that don't require them to know quantum mechanics to benefit from this. So we're going to demand no new programming language. You like Python, you use Python, whatever you like. And behind the scenes, there will be libraries that call on these quantum systems to execute this. But nonetheless, you got to go step by step, right? Before you get to that level of abstraction, you got to build all the other layers, enable them to work, and be able to generalize from there. So let's go and decompose some of these elements, and then we'll finish by saying how we will build these very large systems. So we talked about qubits, and I show you at the bottom the evolution of many families of processors. We name the families of processors after birds, for idiosyncratic reasons. So here's the osprey family. And one of the things that we're very proud of is we're bringing a tremendous amount of knowledge and know-how from semiconductor technology to enable now a whole new generation of multi-layer wiring around that. Our generations of the early quantum processors, they're all wire bonded, they were all in one plane. It really took a lot of know-how to build also, superconducting through silicon vias, the whole level of separation of I/O and wiring to enable this technology to work. So now, that was one of the important milestones to be able to build now processors that have many hundreds of qubit systems. So in fact, this element of being able to do this kind of multi-layer wiring has been really foundational of separation the I/O layer from the resonator layers to couple things to the qubit layer. But where we're going next also is going to be about modularity. Modularity expressed as building many of these quantum processors and establishing connections between these different chips. First, through classical communication. You pay an exponential cost whenever you do classical interfaces. But the next step that we're already working very hard on is also to establish quantum links over short distances, such that when you have multiple quantum processors, you can actually have qubits that span multiple quantum processors. Beyond that, beyond those sort of short millimeter length links, we're also developing longer couplers that in this case may have 30, 40 centimeters on communication. They may be slower in nature than the very short links that we have right now, but it still be able to incorporate quantum information sharing between processors. And over time, build much, much larger systems that would have to span many cryostats and be able to have links that make that connection. For that to occur, we and the field need to develop quantum transducers that allows us to do this coupling over longer distances, which is a very hard scientific and technical problem. But the point I wanted to highlight here is the element of modularity. In fact, the 433 qubit processor that we already built is already pretty big. The one that we're going to deliver this year of 1,000 is probably going to be kind of at the limit, at the largest end of what you can build in a single die for this kind of superconducting technology with the current version of transmons. So the answer for the future, one key message I want to give is that modularity and now system engineering is going to be key. Just like we've seen in classical computers, where we also have many, many chips that are connected to one another, right, through, in racks and quantum intranets, and over time a quantum internet, we're going to see a progressive evolution of increasing system complexity driven by this connection. Modularity also implies that those chandeliers that I showed you with all those like coaxial cables, actually that's kind of like a stuff of the past already on our next generation systems. So why? Because if you have systems with 1,000 qubits, that's a lot of cables. So you need actually different technology to be able to do this, and this is an example of flex cabling and flex wiring that has been developed to be able to do this already, which is going to be incorporated into our next generation of systems. And also, modularity also includes continue to innovate on modular amplifiers and microwave components. There are many, many, many different elements and modules, including many quantum devices that are required to a quantum computer to work. And all of these elements are incredibly important, as well as the control electronics. The first generation of quantum systems that we have, we used off-the-shelf control electronics. You basically needed about $150,000 worth of electronics to control a qubit, like in the early generations, like almost 8 years ago. So now this is a example of next generation of electronics that we have built, with a totally different cost point and performance point that allows us to scale to much, much larger systems. Even this is going to require quite dramatic improvements when we think about having systems that have many tens of thousands of qubits. But enormous progress has been made on that front. And one interesting direction is going to be the world of cryo-CMOS, right? So a lot of the control electronics that generate those pulses, that is the basis of controlling the qubits, there's going to be elements of those electronics that are going to be brought inside the cryostat, and that has a lot of advantages as well. So here you're seeing an example of an early version of a CMOS controller that goes inside the cryostat. So in general, that area of modularity everywhere, modularity of the chips, the connectivity between processors, first with classical links and increasingly with quantum links, modularity in the I/O, and then modularity in the control electronics is going to be a hugely important element to enable scale, because it's not just about building larger and larger chips anymore, right? Is the key point I want to make. The second one, of course, is the all-important metric of quality, right? How well do these qubits obey quantum mechanics, and how long do I have? Just to give you a perspective on one of the measures of the quality inside of a qubit, for the superconducting qubits, the first demonstration of a qubit by Nakamura when he was at NEC at the time, it was in I think 1999 or so. The coherence time was 1 nanosecond. So now on these large quantum processors for superconducting qubits, we routinely build large processors that have many hundreds of microseconds. And then the other measure of the fidelity, what is the average error rate around this? I'll show you, I'll go back to that chart in a second. You're seeing here the evolution over the last few years of the medium error rate of the devices that we have built, and then the best error rate. And basically in May 2016, when we put that first quantum processor on the cloud, it had error rates of a few percent, right? So every 100 operations, you would have 2 or 3 errors or so. And one of the things I want to show you around it, that now in larger devices, error rates in there that we've put out experimentally around that is errors like 10 to the minus 3, right, on those numbers. So 1 in 1,000 operations. And I think there's a lot of exciting work, right, what we're doing there of another factor of 10 that is going to be doable in the next few years. So by the time you get to error rates of 10 to the minus 4 for these superconducting technologies, and you have coherence times that are in the many hundreds of microseconds, and you have devices that are big enough with 100 plus qubit, it's a very interesting regime, and I'll go back to that. And one way to sort of like measure that is this integrated metric of quantum volume that integrates many of those factors. And you're seeing here how it has progressed. We had the goal of more than doubling quantum volume every year, and you see here the experimental progress that we've made in that field. But I want to give you some of those numbers that building for superconducting technology, chips that have hundreds of qubits with high coherence and error rates on the order of 10 to the minus 4, that's a very interesting neighborhood with which to do exciting things, and more of that in a minute. And then the third element that is very important, because to run any practical applications, you're going to have to run many, many, many circuits, right? So it's not just one runs and around that is, how fast is it? How fast is the machine? How many circuit layer operations per second can you do? And this is an area that to really optimize this, you have to optimize everything from the qubit technology that you choose. Incidentally, that is one of the key reasons we like superconducting technology compared to other technologies like ions, because they're much, much faster than ions, as an example. But also, you got to optimize everything from the compiler to the control systems around them to reduce overhead, etc. So this is another area where we've made a tremendous amount of progress on how fast the machines are now in being able to execute practical circuits. So if you just get a sense, just to give you a feel for what progress is looking like, it's like, over the last year, we've increased the number of qubits by a factor of 3x, the quantum volume by 4x, and the CLOPS operations by over 10x. So that's all good and interesting. But, what's next? What do we have to do in the years ahead? So what's next, as I mentioned, is modularity at every possible level. So in fact, it's going to have to be an approach where we're going to have to bring a system engineering perspective about blending classical information and quantum information natively, right? This world of bits and qubits coming together. And that's our vision for creating quantum-centric supercomputers. So, and think about it just by analogy. We've seen an era of CPU-centric supercomputers that we had for many decades. We have seen over the last decade GPU-centric supercomputers. And, sort of by analogy, it's definitely going to be possible to create quantum-centric supercomputers where we're going to exploit all the other previous architectures and combine it with these kinds of systems. So to be able to do this, we really need to build systems and software that seamlessly integrates classical and quantum information to be able to extract the most power of these devices. And the way that that's going to look is basically you're going to start with your program. And the first thing we're going to do is this piece of using classical resources to compile. Now, this compilation step is expensive, right? There are many different ways to implement those circuits. And let me just go a second so you see around that. So there's going to be this long sequence of gates and compilation that happens. And one is going to have to be very judicious about how you actually cut that very long circuit and parallelize the execution of that circuit. So the way we're going to go about blending this is this parametrized circuit has a very large length. We're going to decompose it into many circuits, and that choice is actually a really sophisticated and nuanced mathematical problem. Once we separate into many different quantum circuits, we are going to send them in parallel to a cluster of many quantum computers that are going to work in parallel. So each one of those circuits is going to run on different quantum processors. We're going to get the answers from each one of those quantum computers, and then once it comes out, we're going to use again classical resources to reconstruct the result and bring an answer back to the user. And we're going to do this iteratively through many, many, many loops. So the point here, to make the point, is it's no longer about having a single processor that runs a circuit and I get an answer and we're done. The point I'm trying to bring across here is actually a very large-scale engineer system where you're going to bring to bear lots of classical resources along with multiple quantum processors, all needed to be orchestrated in the calculations. So the game, of course, and the path is how do we can use and exploit these resources to be able to advance and achieve some form of quantum advantage, where we start doing some calculations more efficiently or cost advantageously that we can do with classical machines. So how will we go about doing that? So, well, the first thing is we got to focus on problems that ultimately are going to deliver some form of super polynomial quantum speedup, right? I mean, if we're picking problems that, we're going to have marginal advantage compared to classical machines, let's just bet on classical machines to deliver that, right? Because we're very good at making those machines better. So focus on the problems that have the right mapping to something that will deliver exponential advantage. At the beginning also, we got to focus on less expensive heuristic version of the algorithm. I think the field historically was very anchored on having algorithms that have a lot of formal proofs. But let me just make the point, in a field that is going through a lot of excitement like AI, it's not characterized by strong theory predicting all the results. It's as heuristic a field as you can imagine and still delivering tremendous levels of advancements, right? So let's not minimize, when you put it in the hands of a lot of smart people, the power of heuristics to deliver advantage. Now, those heuristics have to be mapped to circuits that can be exploited for near-term hardware that we actually have, and not computers that we're going to have 20 years from now, but the ones we actually have right now. And the last element is that well before we have full error correction techniques, and more of that in a minute, there are actually a whole host of error suppression and error mitigation techniques that are really interesting and powerful if you can characterize your system. So in some way, if you say, what is the path to achieve quantum advantage? We have this chasm, right, between near-term systems that we have, of the quantum computers we can build and the theory algorithms that we have. We know ultimately we will get to fault-tolerant quantum computers, and we have proven and known algorithms that will deliver exponential advantage. But the question is, what's in between, right? And what is in between is we're going to have to figure out techniques to deal with the errors that are present and exploit current capabilities to do that demonstration. So we know that in quantum computation, we must deal with errors. Errors come from the fact that the outside world couples to our system, right, and affects or destroys ultimately our very delicate quantum information state that we have created that we want to control over. So these errors that are present is we have a variety of techniques that we can exploit. So one very interesting technique is error suppression, in which one of the things that we have available to us is we can modify the circuit however we want. We can add gates to it, right? And one particular interesting technique is, without changing the individual meaning of the circuit, the ultimate algorithm that you want to implement, you inject additional gates to actually echo away particular errors. And there's ways to be able to do this, and I'm going to give you just a sense of one example of how you can do this. So one of the things that you can do is a technique called zero noise extrapolation, and it actually has a simple intuitive field that you can, the computer is operating with certain errors, and then you send your computation and you get a measured expected value. But one of the things you can engineer is you can control the pulses that you send into the machine such that you can inject more noise into the quantum circuit. By injecting more noise, you run the calculation again, and you get a different answer where it's at a higher noise level. And from there, you can then extrapolate what will be the zero noise point to be. It's a simple extrapolation, right, based on having 2 points where you're running the device at different noise levels and then extrapolate back. And if your system is well characterized and stable, you can actually use this to get results. And I'll show you a result in a second. In fact, you can do this over many circuits, and have something called probabilistic error cancellation, where you are injecting additional gates to reconstruct the noise inverse around it. And I'm putting here a number of citations for you to look at. The point is that you can actually use these techniques of error mitigation and error suppression to actually compute circuits with an increasing number of depth. So here's an example of a 127 qubit system with a depth 60 in terms of the number of circuits that has been error mitigated in the present. So if you have a good understanding of the device that you have built and the system, well before you have full error correction that has a high degree of overhead, you can actually implement ways to mitigate and suppress errors in ways that is quite powerful. So I'll point here, and happy to circulate later, some of these techniques, because I think it's really interesting what is evolving in terms of error suppression, error mitigation, and ultimately error correction. So what I think is going to happen, right, and what the team is betting on, is think about it from a perspective of what is the simulation cost as a function of quantum circuit complexity, right? Like how deep a circuit you can run to solve practical problems that you care about. Ultimately, we're going to get quantum error corrections, where as the simulation cost, as you increase the mapping of these complex problems that you want to be able to solve with computers, with classical computers, you face an exponential cost. Ultimately, once we have quantum error correction, we're going to have systems that have a linear cost increase as we increase the complexity of the problem we're trying to solve. But before we get to the error correction, full error correction regime, we are going to traverse another curve that has a shallower exponential. And that is going to be driven by the utilization of error suppression and error mitigation techniques, and partially error correction, right, for subsets of the circuits that we're running, along with a very significant use of classical resources and parallelization. So the goal over the next couple of years is to make that switch, make that transition from the current exponential cost to a new cost that is going to be enabled by this generation of machines. And just to give you a sense, we've issued this, we call it the 100 by 100 challenge. So the goal is to deliver a capability to our community where within the next 2 years, we will offer a system that has 100 qubits and depth 100 that has been error mitigated and error suppressed. And if you look at that, and these are experimental results and publications that are either in print or coming, where you're seeing here that we are going to get to this land. And in this land, we have, frankly speaking, I think a strong confidence that there will be demonstrations using this capability that will enter the first realm of, first examples for scientific applications of quantum advantage. So our belief is that, before we get to that journey of fault tolerant, that we're going to see this continuous evolution of increasing more and more capable systems, where error mitigation is going to be a core technique that is going to be implemented into that, and that the combination of all of these techniques with large-scale parallelization of classical resources and quantum resources is going to be the journey that we're going to traverse before we're able to build, full fault-tolerant quantum systems. If you're a little bit, more interested, obviously there's lots and lots of publications in this field, but I'll point you to this paper that we recently published on the future of quantum computing with superconducting qubits, where we explore a lot of these ideas in more details. And I'm going to close with the system that we're building, which we're calling IBM Quantum System 2, of which we're going to have the first prototype instantiated this year. And this is the example of a system where we've gone back to the drawing board on modularity for everything. Much larger cryostat. So, this is now things that you can walk into, right? I mean, in terms of volume. In fact, in there, we're going to have now multiple chambers inside the cryostat where multiple quantum processors are going to sit in concert. We're also designing it so that multiple of these systems can be connected through different configurations to establish these links between the different quantum processors. We've designed it also such that very significant amount of classical computation is going to be present, co-located with the systems around this, because as I mentioned, parallelization is going to be key. Right? Large circuits broken down into pieces, parallelized on many quantum processors working in concert around that. And, that's a system, like I said, that we will have, a first prototype later this year. So I'll close with an invitation, right, to continue to work. Part of this journey is not only to create amazing technology, but to do things together, right, as a community. And I think that's one of the great joys that I have visiting here at Berkeley with good friends like Irfan and others, which is, how do we continue to advance the field together? But I wanted to give you a perspective at least of what we're doing in IBM Quantum. And thank you very much for the invitation. Yeah. So look, our commercial vision, right? It's a good question around that. So the first market that we are serving is the world of R&D, right? And you say, well, is the world of research and development really a market? It's like it is, you know. I mean, the world spends, you know, depending on different nations, but 1.5%, a couple percent of GDP on R&D. Quantum technologies has become a priority in many countries around the world. And first and foremost, this is a new scientific instrument, right? Lots of universities, national labs, people around the world want to have access to these resources. So we are in the business of providing computational resources, both deliver as a service and for people that want to have a dedicated quantum computation center, which are many countries around the world that are doing that. I give you examples. We're actually capable of installing and delivering really high availability systems that have, you know, 99% plus uptime to regions and countries around the world. So people pay for that. They buy our machines, and they build programs with us around that. The industrial sector also pays for this. I give you a list of many companies that work with us, where you're starting to see, you know, putting small teams, right? I tell people you shouldn't have hundreds of people working on this, but if you're in a business that relies on computation, hey, if you can tolerate, you know, a horizon the next 5 years plus, you should have a small team that starts to think about it, and many are doing that, and people engage with us and partner with us on that. So that's the first market. We have to then cross the realm of, you know, starting to demonstrate abilities of quantum advantage for then larger scale sort of utilization of these systems for production sort of environment look like, right? So that's kind of what we're doing, and then building a community as we go along. And I'm not going to comment on, you know, other, you know, stuff. What I will tell you that I very strongly support the emergence of a healthy and vibrant quantum industry, right? I think it's really good for different people to take different, you know, approaches to the technology, take different levels of risk. The thing, you know, I'm passionate about is that we're grounded on where the technology is, that, you know, that we are scientifically, you know, driven around this, and then advance the technology. But I think it's really healthy and good to try many different approaches, and, you know, and that's one good example of it.
So thank you. My question is a bit of a follow-up to that question, actually, about the kind of the federal funding history, because it was a fascinating presentation. I did attend, you know, kind of similar presentation maybe 20 years ago, and much of the deck could have been exactly the same, other than the, you know, kind of like new updates to the systems. I'm just curious, like, what has been the regimes of federal funding, and how much of it, if any, is private funded? You know, just maybe within the nearest 10 billion. I don't know if you know that. And this was a final footnote, if, you know, depending on what you can say about that. I remember seeing a news article a couple of years ago. China had claimed they made a quantum computer. So wondering if you could just comment on how realistic that achievement was.
Yeah. Okay, so I think on the realm of federal funding, and answer generically in the United States, but also around the world, I would say funding less than like 4 or 5 years ago was, you know, relatively modest, right? In terms of like open funding for the scientific community. I wouldn't say that like quantum computing and quantum information was like a top 10 priority for most agencies. I think that has changed a lot over the last, you know, 6 years or so, 5 years. In the United States, the National Quantum Initiative was one good example of that, where there was a bipartisan bill, and there were, you know, I can't remember exact amount. Was it a few $1 billion, if that? $1 billion were allocated around that. There were a set of NQI centers that were established with DOE and different ones, and so on. So, but, you know, that was over 4 or 5 years, so it gives you a sense of a couple $100 million a year, you know, on that order around that. In the EU, there's a flagship program too, €1 billion program around that. In China, there's been like, you know, it's very hard to know, but there were like published, you know, people reported numbers that they had like $10 billion program or whatever it was. So, you know, on aggregate, many multi-billion-dollar programs at the level of federal government and so on, right? Then there's the private sector, right? And I would just distinguish sort of two categories, sort of like large technology companies that have self-funded programs around that, So if you ask, like, who's paying for all of this, we're paying for all of this, right? So this is not, we're not dependent on a lot of the things today around the scale of things, like the lion's share of this is being corporate funded. And then there's a venture capital piece of it, of which there's been quite a bit of activity over the last 4 years and is going through its cycle, right, of, a lot of exuberance, right? And now, honestly speaking, there's tough times for a number of startups, right, of going through this, because this is not for the faint of heart, right? It's an expensive technology. It's going to require long-term commitment and large-scale teams and very sustained funding to be able to achieve the objectives, right? So hopefully it partially, at least answers your question on that.
Thanks for the amazing talk. I'll kind of follow up on that. Like you mentioned, it will require long-term programs. There's a lot of challenges. So there's lots of open scientific questions, starting from materials, devices, packaging, interconnects, on all of these fronts.
Yes.
So what do you think is a good way to communicate the challenges you're running into with the academic world, and how can academia help?
Yeah. It's a great question, and I think it's a very important question that we have to address, in the near term. And what I mean by that, and in fact, this is a piece of active collaboration also that we have, right, on trying to imagine a way to be able to codify some of the nature of those problems and publish them, right, and make them available so that there's a bit more transparency as to, here are hard problems, or maybe by the absence of listing other things, maybe these are problems we've already solved, or, we're already committing on solving of it. Because I do think that that's very important, because there's a lot of, across the world in this field, a lot of duplication of work that is, sometimes unnecessary or poor definition. And there's been many examples of doing this well in the past, for example, in semiconductor technology, right? Where the presence of roadmaps, the clarity as to, when you had to deliver a certain capability to be able to intersect a node, in the case of semiconductors, like all the way down to materials. In my old field of lithography, is like, hey, if you're going to develop a photoresist, it has to be able to deliver this lineage roughness on this date, for this wavelength, and you either have it ready or it's just not ready and not going to be incorporated. Of all those components that we talked about and something, where is that for quantum, right? It's in the realm of people building these technologies, but it's not broadly shared. So I think you raise an excellent point, that this is something that I think can be the basis of providing more clarity to the overall community. And then, faculty and students and so on can also pick from that catalog of problems and imagine solutions for them. So that's at one level that I think is really important for the field to advance. I think on the other level, too, is to be inspired by, kind of like national capabilities, or however we want to put them. And this is where I was laying out that vision of quantum-centric supercomputing, right, that we've been developed, is in addition to the individual components and individual materials advances and so on, we should also have our sights of building, many, many generations of increasingly capable systems. And in the field of computing, with supercomputers, they played an important role in the world of computing, because it allowed us over many decades to bring together at particular moments very advanced computational capabilities that push the limits of processor technology, networking technology, memory, software stacks, etc. So I think that's the other parallel, like clarity on grand challenges and at the specific, modules, materials, devices, packaging, etc. But also oriented towards, a capability that we could build together as a field and demonstrate, just like happened in supercomputers in the past. So that combo maybe would be really promising for future NQI, future next generation of however we coordinate systems between public and private sectors.
Well, maybe we should stop there. I just want to thank you for such a really inspiring and exciting talk. I'll just comment. It's really exciting to see IBM, taking the lead so far in front of the rest of the world, really. It kind of puts me in mind of, the IBM that we all remember being such a great pioneer in so many developments in computing. The IBM PC, I like to give a little talk about how that is the most amazing consumer product ever developed and introduced in the world, in history. And I think I'll be looking back on this talk in future times to the presentation that you gave today, offering such a really exciting, dynamic, and new perspective on the prospects for quantum computing. So thank you so much.
Thank you so much, and thank you.